All right, so to start, let me use the document camera here for just a moment. Camera on. Well, I don't know why that's not showing up. Tell you what, let me see if I can do something different then. Okay. Oh, too large. All right, so what I want to do, sorry about the delay here. I seem to have a problem with the projector when I switched it over to the document camera option. Let me start by just quickly reviewing the key pieces of the Solow Growth Model that we put together in the last class. So remember that there are three kind of main ingredients you need to understand. The first is this thing that we talked about at length called the production function, right? Which shows how a country's level of output is related to its underlying stock of capital, right? We denoted the production function with this f of k term. The other piece of the model was the investment and the savings schedule that looks a lot like the production function, except it's sort of rotated down a little bit. And the reason why is because we're assuming in this model that investment is a constant fraction of our economy's output of goods and services every year. And that fraction was denoted with the parameter gamma, right? And output, of course, is the same as f of k. That tells us what the production function is. The third ingredient or piece of this model was the depreciation schedule. And another key assumption in the Solow model was that depreciation was just a constant fraction of the capital stock. Having all kinds of mechanical problems today, it looks like. Okay, that depreciation rate was delta. So what happens according to the Solow growth model? The capital stock is going to rise or fall over time, depending on whether or not a country's level of investment exceeds its level of depreciation, right? If investment is bigger than depreciation, then the forces that are tending to increase capital outweigh those that are trying to decrease it over time, and the capital stock will rise. And vice versa when investment is smaller than depreciation. And we know that eventually the economy should converge to what we defined in the last class as a steady state value of capital that occurs right here at the intersection of the investment schedule and this depreciation line. We can identify what the steady state level of output is by tracing up to the production function and then over. And what is steady state consumption then? It's just the difference between output and investment. Right? That investment share parameter determines how output is kind of allocated between consumption and investment. Okay? That was kind of the conclusion of what we talked about in the last class. We did all of this graphically. We talked at length about where all of these curves came from. We talked about this concept of a steady state equilibrium. And then we also, I know we just had a few minutes at the end of class, but we worked a version of this problem where I provided you with actual equations instead of just the graphs to solve for the values of K and K star and Y star. Okay, let me, I wanted this to go a little bit more smoothly, so I apologize for this. The one major implication of the Solow growth model that we just graphed a minute ago is that capital accumulation by itself cannot possibly be the source of sustained growth in the very long run. Okay, and I want you guys to think about this for a minute. What does the Solow model tell us? That over time, diminishing returns are going to set in, right? So even for a poor country whose investment is bigger than depreciation and whose capital stock is rising, those additions to investment are going to slow down over time because of diminishing return. Depreciation, on the other hand, increases at this constant rate. So you eventually get to a point where output and capital converge to this fixed, steady state point, at which point things like output and the capital stock are no longer going to be growing. So while the economy is transitioning to the steady state, your economy will experience positive growth in living standards. But what that simple little model and the graphs show us is that eventually, once an economy reaches the steady state, all else equal, output's not going to get any bigger. And so we would expect in the long run then, according to that model, for the growth rate of output to eventually settle down to zero, right? Where output and capital are no longer growing, okay? And all of that follows from this law of diminishing returns. The model, as we've discussed it so far, however, I think does a pretty good job of explaining this idea of rapid catch-up growth that we see in countries like China. Poorer countries that are at an earlier point in their growth trajectory, it's most likely going to be the case that their investment will be a lot bigger than depreciation. And so capital will tend to grow, and as the capital stock grows, you're going to witness high growth rates of output, right? So as the economy moves towards its steady state, we witness this idea of catch-up growth. And so I think the model does a pretty good job of explaining that part or that aspect of growth. What it doesn't do a very good job, however, so far I should say, is explaining this other type of growth that we talked about in the last class, and that is frontier growth. If you guys take a look at developed countries like the United States or Canada or many countries in Western Europe that are presumably much closer to their steady states, they've been growing for a lot longer, it's still the case that those countries tend to have positive growth rates in output over time. What that means then is that our model is kind of insufficient so far. It's missing something that can explain that frontier growth that we see in the developed world, okay? Now, there are a couple of possible candidates for how we could explain this. One of them you might think is human capital, right? We've talked about physical capital in this model a lot, but what about human capital? That's this knowledge and skills and experience of the workforce. I think increases in human capital can probably raise GDP and living standards in the short run, but one thing you've got to remember here is that human capital is very likely going to be subject to diminishing returns, just like physical capital is. So it's not likely going to be the case that if we put human capital in the model, or we allow for changes in human capital that somehow that's going to allow countries to escape this kind of logic of diminishing returns, that there's something else must be going on. And I'll go ahead and get directly to the punchline here. The component of the model, or the concept that is going to allow us to escape the logic of diminishing returns, is technological knowledge. In particular, improvements in the production process through gains in technology over time. Once we modify the model to account for better ideas over time, we'll be able to more clearly explain or distinguish frontier growth from catch-up growth, which is what we've talked about so far. Okay, one of the useful things I think about the Solow growth model, because it is a formal mathematical model of long-run growth, is it allows us to provide some insight into all of the potential forces that can potentially drive living standards higher over time. Okay? In the short amount of time I have today to talk about this, I want to discuss two potential forces or factors that might cause things like capital and output to actually grow over time in the context of the Solow model. The first one I want to illustrate is, I want you guys to think about what might happen if our society, or our economy rather, were to increase the number of resources that we devote towards investment and saving every year. Okay, so in the examples that we've been working through so far, we've assumed that this investment fraction of output was 30%. I want you guys to do the following kind of thought experiment, and then you'll have a chance to work these on your own in today's extra credit assignment. What happens if we all kind of collectively decide that we're going to start saving more and investing more in new capital as opposed to just spending on consumer goods and services? We can think about that in terms of an increase in gamma from, let's say, 0.3 to 0.4. Can this potentially explain why developed countries like the US are able to grow even in the very long run? Well, let's see what the model has to say about that exact question. And for this, I want you guys to talk this through with me, okay? Where do we start? Here's a good starting point. If you encounter a question like this on your exam, which asks you to apply the Solow growth model, the best place to start is to draw the three graphs that fully characterize the equilibrium in the Solow model. So what do we have again? The production function, which was y is equal to the square root of k. We have the investment savings schedule, which in this case is 0.3 times y, or the square root of k. And then we have our linear depreciation schedule, where we've assumed that depreciation was 2% per year. In the steady state, we know that investment is equal to depreciation, which occurs right here at the intersection of these two lines, right? And as we saw in the last class, that gives us a steady state level of capital equal to 225 and a steady state level of output equal to 15. Okay, I want you guys to help me out on this. Imagine I ask you on an exam, what happens if our economy here decides to save and invest a larger fraction of our resources? We go from 30% investment now to 40% investment. What happens to this economy in the long run and also in the short run as a result of that change? And be disciplined about this. Ask yourself what would happen to the graphs here, and then think about what the equilibrium change would be. Sean? Well, let's take this one step at a time. What changes on this picture? The investment schedule is going to shift up, right? So if it's now 0.4 times the square root of k, the entire investment curve kind of rotates, what, counterclockwise, or shifts up from the origin? Good. All right, so Sean, And let's take this one step at a time here. Let's say that we were initially at this point where our capital stock was 225. It was the case that investment was equal to depreciation. But now, investment is bigger than depreciation. So what is going to tend to happen to the capital stock then in the next several years? It's going to go up, right? The capital stock is going to rise because investment is bigger than depreciation. So what we already can tell here is that if we permanently raise our investment share to 0.4 from 0.3, that is going to set in motion a period of rising capital, right? And as the capital stock goes up, output is also going to increase along this fixed production function. So we see here that at least in the short run, higher investment and saving will allow the economy to grow more quickly, at least temporarily, okay? Now, Sean, what do you think eventually happens here in the very long run? And when we're talking about long-run growth models, we don't mean periods of just months or quarters, or even really years, but this could take decades. Well, so consumption is the difference between the production function and investment. So that could change over time, sure, but what do you see happening here? That as capital grows, investment is going to increase, right? But at a decreasing rate. What's happening to depreciation? It's increasing at a constant rate, which means that diminishing returns will eventually set in and we're going to reach a new steady state equilibrium, which is the intersection of the new investment curve and the same old depreciation schedule, which occurs, if you want to plug in the numbers, at a capital stock of 400, so we're a lot richer now, and a steady state level of output equal to 20. So what this experiment shows us then, or at least what the Solow model would predict, is that higher levels of investment will increase output, but it's only going to increase the growth rate of output in the short run. The growth rate of output will be positive as you transition from this point to this point. But eventually, the economy is going to settle down into a new, permanently higher steady state. So yes, we will get richer in the long run, but we're not going to experience positive growth in living standards in the very long run, only during the transition period. Okay, so let me kind of summarize what we have on that graph here on this slide. The results of the previous diagram are going to predict that an increase in this investment rate causes output to go up. That also causes output per capita to increase because we haven't talked about changes in the supply of labor, right? So living standards or average productivity would grow as well. But we did make one important observation, that this increase in gamma just permanently raises the steady state level of output. It does not, however, increase the growth rate of output permanently. At the old steady state, the growth rate of output was 0, and then the growth rate of output was positive for a while and converged back down to 0 once we got to the higher steady state equilibrium, okay? So the conclusion here then is that higher investment and savings cannot actually explain why rich countries like the US experience positive growth in living standards over time. It must be something else. Even if we saved 100% of our income, we're not going to be able to sustain that growth according to this model, that we eventually settle down into a new steady state. So where the growth that we actually see in the US economy in the long run of like 2% per year, I showed you guys data on this some time ago. Where does that come from? Where can we trace its effects to? Well, I think the answer to that, of course, lies in understanding how technology improves living standards in the long run, okay? And so that's the second example I want to use the Solow model for. Okay, the first thing we need to do here is ask ourselves, how do we want to think about or model, in a mathematical sense, improvements in technology in the Solow model? Okay, we're going to do this in a fairly straightforward manner. When we talk about technological improvements, what exactly do we mean? This is kind of an abstract idea, right? It's not something that is really easy to define. But the basic idea with technology is that you would say that a country's technological environment is improving if we're able to produce more units of output using the same number of actual physical inputs, right? So we have some amount of labor and some amount of capital. If we all somehow get smarter and invent new technologies about the production process, we can produce more goods and services given the same amount of inputs. That's how we think about technology. Well, it turns out we can incorporate that idea directly into the production function. You guys remember early on in the last class, we introduced this variable or parameter A in the production function to represent or denote technology. We kind of ignored it temporarily. Well, let me reinsert it back into the production function so that we can talk about changes in technology. Imagine for a moment that the production function looked like this. Output is equal to A times the square root of K, where A is this kind of index that summarizes the state of technology in our economy. What have we assumed thus far? That A is just equal to 1, right? And we've kind of ignored it in our analysis. Well, let's think about this for a second. If A is equal to 1, and let's say we have 16 units of capital, then how much output do we produce? 1 times the square root of 16 is 4, right? Well, what if I told you that the state of technology doubled? We're all of a sudden twice as smart as we used to be. Then those same 16 units of capital, where A is equal to 2, now produce 8 units of output. See how easy that is? This is how we're going to model or think about improvements in technology in the Solow Growth Model, is by augmenting the production function with this little parameter A here that we can change, and it's going to shift around the production function. Simple enough? Okay, so here's the second question I want to ask you. Let's suppose that there is a 50% improvement in the state of technology in our economy. We'll just describe that as a move in A from 1 to 1.5. How does that affect the growth rate of this economy, both in the short run and in the long run? Again, I want you to think about this using the graphs of the model, where we have a production function, this investment schedule, and our depreciation schedule. The steady state level of capital, again, is initially 225. And so this is the initial output level at point A, equal to 15. If technology improves, what happens to this picture? Matt? A enters the production function right here. So if A is bigger, 1.5, it's going to shift up the production schedule. But notice something different about this exercise compared to the last one. Because it shifts up the production function, Matt, it's also going to shift up the investment schedule at the same time, because investment is just a constant fraction of output. So both of those schedules move higher. Now let's ask ourselves again what happens here. Let's suppose this was our starting point. Here, investment is equal to depreciation. We have this improvement in technology. Now, investment is bigger than depreciation. So Matt, what's going to happen in that case is that the capital stock will start to increase as a result of that, right? And as capital grows, what's going to happen to output? Output is going to grow until we get to the new steady state equilibrium, okay? So one of the differences between this exercise and the last one is that in this example, output really grows for two reasons. It grows because the capital stock is getting bigger, but it also grows directly from higher technology, right? So improved technology and growth in capital cause output growth to be positive, okay? Now you'll see on this graph though that we kind of have the same situation that we did in the last exercise, right? As capital grows, investment gets higher, but at a diminishing rate, whereas depreciation goes up at a constant rate. So the logic of diminishing returns says that we should eventually get to a new steady state point where investment is just equal to depreciation. That occurs at a capital stock of around 506. Again, I would encourage you to put the numbers in yourself to verify it, with an output level of about 33.7. But what is the difference between an improvement in technology and an increase in savings or investment? Why? Perfect, right? The most that you could possibly increase output in the last exercise would be if you increased gamma all the way to 1, right? You can't save more than 100% of your output. In principle, there is no limit to how much technology can advance over time, right? And in practice, what do we actually see? Every year, or at least every few years, there are general improvements about the stock of ideas and technology that cause this A parameter to continue to rise. And so what happens in the real world is that the production function and the investment schedule are continuously kind of shifting up, and it pushes even developed economies towards ever higher and higher steady state levels. That is frontier growth. The way we discriminate between frontier growth and catch-up growth in the Solow model is that catch-up growth is about increasing capital to a fixed steady state. That's what developing countries are experiencing and is why they can grow rapidly. Frontier growth is slower and more difficult because it's really about improvements in technology that continue to push up the steady state over time. That happens more sporadically, okay, and explains why developing countries like the US have slower growth rates in living standards. So the Solow model, augmented with technological improvements, can explain both catch-up growth and frontier growth. And that's all I have to say about that. Guys have any questions? Matt? Yes. Yeah, so remember, one of the assumptions in the model is that investment is just a constant fraction of output. I'll tell you what it is. If not, you can just say it's gamma. It's just some number between 0 and 1. Yes, yeah. Okay, why don't you guys, I'll have a chance to examine, kind of test your knowledge of the steady state and how the economy transitions to the steady state by working this exercise. If you will, upload the Excel worksheet to your computers. Maybe you've already done that. I think it's called Solow Model or whatever. And then there's also some instructions that you can get from Blackboard, or I can hand them out to you directly. What I'd like you to do, so the instructions are pretty clear. Just follow these, and I'd like you to provide answers to the questions directly on this piece of paper. And this is what I want you to turn back into me either today or on Thursday, okay? I don't need you to email me your completed Excel file. That's for you to keep and to study from. All right, and then I'll kind of walk around the room and give help where needed. And I'll also kind of fill in the Excel sheet up here as well so you can kind of check your answers, okay?